Hello everyone. Today we will do a time history with robots. I will use as base the French regulation about pedestrian bridge done by French states. So here we'll go on the page 80 and you have the definition of the pedestrian bridge. So you will have the detail on village bin and you can switch the language. So here in the previous article, I do this analysis with a frequency domain, harmonic analysis, which is better. Here we'll do in time history um, in order to explain how time history work in robot. Okay, it's I would say the simple case you can do. And you have the link of the regulation here. Okay, so here you have the length of the bridge. I try to do the same in robot section, but I don't find exactly the same inertia. So I will create a simple beam with this inertia. So I do from beginning to the end. Of course, then I will put some support. I will create load cases first, and then I will create some support here. Here I will remove the automatic self-weight. I will put my loads in Newton, okay, here because I already prepared it in Newton, in kilonewton by the way, in my article. So I will copy paste this value and I add the load. Okay, and by the way, you can change where you want. For example, if now I switch forces in kilo, which is not so logical, but anyway, you can do it. Here you have exactly what is taken into account. So I will switch back to kilonewton and I will add my load in live load, which here I will take the full loads. Even if you will see after, because it's class 3, we'll take only half of this word for frequency. So here I copy and then I paste in robot from the same way. I add in self-weight, in live load, I add this value and I add to my beam 1. I will add a little bit more node. Here I have 2 nodes. So I will create some nodes. Here I will use that. 20. Okay. And I will rename number. So I will take this as the first, second, and 3. Okay. The other one, it's not so important. So now I will create 2 modal analyses, one only with the self-weight and another one with half of the pedestrian load. Okay, so here I go here, I create a new modal. So I want to take the density. Here I can let all, I will put 6%. Okay, and I will create a new model. Okay, with half, so same here, dumping 6%. Okay, and here in load definition, so here the first one I will add to global mass. Global mass, it's the mass which is used in any, I would say, analysis. And dynamic mass, it's the mass which is used in only dynamic analysis. So both I will add. And for the two, which is the live load, I will add it only to this model analysis with the value of 50%. Okay. So now, so I can run my analysis. So I can go in result, advanced model, and here I can have my only in self-weight frequency, and here with half of the percent here, and we can check we have the same frequency as in Excel here, and well, I would say in the grid, but here there is a typo error, so we don't have the same, but it's really 208. Okay, so now we have the frequency. We will go to the time history analysis. So at first we need to define the direction and the value. So here I will create a new case. So 5, it will be kind of live. Okay, I add, yes. Well, maybe I will rename tempo for time history. Here, it will be more easy to understand. And here I will put only on my members 1 Newton and like this. Okay. So now I have defined the load we will be used for time history analysis. I will define my time history analysis. So here I go there. So I create a new time history analysis here. And so at first, so I will set the time. So since the length of the bridge, I take an average speed. It gives me sometimes, and I increase a little bit to find the value. It was quite written, well, not exactly like that, but it was the spirit in the regulation. Okay, and as step, you, in fact, well, at the end, it's sinusoid and cosinusoid will be used, and so you need to have this shape. So you need 20 points of integration at least. So if I take the smallest period, here I have this value. So at the end, it can be smaller. And if I look, I can have this. So I take this one as element, which is really smaller than this to be sure to have maximum. Okay, and division, it's the number where it will be saved the result. So because I want to have really a smooth diagram, I will do this. So here, so time step division 1, I save every single, and 80. No, here I won't go for P delta and large displacement. So next, I will use modal decomposition. I will select for each mode the damping. Okay. Of course, you can set the first and the 10, for example, and it will be extrapolated linearly if you want. But here I will do. So here, model decomposition. Uh, 99, in case. Okay, so now I will go in my function definition. So I will call it village beam live. I will add it. So here I will go to point and I will add expression. So if I come back here, so this is the expression in Newton. Okay, so here I just have to copy paste here. And it's important to copy paste it. It means write it before on Word or any document, because after you won't have access to it. Beginning 0 and 80 time step, I choose the same, 5, and here I put P, so in radian. So, okay, and it creates my element, but since it's quite long, we can't display it. But it's not a problem here. After you can go at the beginning, in function, and you can save it in this value. So if I come back here, function, I save to file beam live. Okay. So I will open a new. So this here, it's space. Here, finish. So here you have the value. And for example, I could have a check. So if I come back here, I can take my expression again. I will do here. So here I have to switch between dot and comma here. Okay. And of course, as you imagine, we have the same. If you are not sure, maybe to the digit like this. Okay. So of course, this kind of Excel text file can be used in input the time I create the graphical. So if you have this time history as a input, you can just load them. Here I use it only to verify, but you can do in both direction, as you can see, because you have the load button. Just before going in calculation, here I use the modal decomposition. Just if your time history analysis is defined in displacement, velocity, or acceleration, you need use HT or Newmark acceleration method. Okay, the modal decomposition won't work for this. Okay, so for these two, in fact, with Newmark or Newmarked acceleration, you will set two pulsation here, and after you give the damping, and you say calculate, and the robot will calculate for you the alpha and beta value. Okay, and for this methodology, okay, HTT, Rayleigh coef alpha by default it's minus 0.3, but it has to be validated. Okay, so now let's come back. So we have done the Excel. Well, we won't give any factor. since I put only 1 Newton in the load case, you see I could have put 1 kilonewton and here 0.001. It would have been the same as factor. And shift phases, if you don't want to start by maximum, we could have shift from half a period, for example, or something like that, but I won't do it. Okay, and I will add it here. So here I close. Here I select my tempo. Here the function 0 add, and it is done. So here I just select, verify that I have done all. Okay. And now I can run. On my computer, I think I write to you. It will take 1 minute on my Lenovo ThinkPad P16G2 with 64 gigabit read-only memory. Okay, now it's done. I can save here, and I will go in result, advanced load history diagrams. So here I want the acceleration. Node, it's node 1 that I want. Add. So this change the color. Apply. I will not scale here. So solicitation, and here the acceleration in node 1. So we can see after yeah, it increased, but after 40, yeah, maybe a little bit more. 50, we have something which seems to be quite classic. If you want to zoom on some part, here you can go in not automatic range, and you can do that, and you can see here. By default, automatic range, it's all. And for example, if you want really from that to that, you have this. So you see we have a lot of integration points, so it's quite smooth. So here I scale the two value to it's the definition. So here I will go in result, advance, and table, and I will go for the envelope here. By the way, I want better units. So here, if I look here, we have 289, okay. In Excel, I have 288, okay, and here 288, yeah. So it's quite accurate, and here I have the definition. I just want to see if I don't forget. Yeah, you can. We could have choose different units. Sometimes it scales better, depending on what you want. And yeah, something interesting. The maximum at the end, we can see here. It's for this time step. It means that it's nearly the end. So maybe 80 seconds was quite good to be sure to be in the real value. Here, yeah, so it's really nearly the end, I would say. So thank you for watching.